Thank you for the introduction. So as James mentioned, my name is Griffin Dietz, and in my work, I integrate perspectives from HCI, cognitive development, education, and AI to design and develop cognitively appropriate computing education platforms for young learners. So in recent years, we've seen a global push for computing education for all children, for whom this early exposure can lead to increased interest in the field, the development of computational thinking and literacy skills, and computing readiness to support an entire educational career. And with the growing influence and prevalence of AI and machine learning in everyday life, we see both new opportunities for delivering educational content that leverages AI and new obligations to educate young learners about this kind of technology that they interact with every day, continue to do so more and more. But there remains a lack of AI-supported computing education tools. A number of computing education tools do exist, but many students still lack access because those tools don't meet the cognitive needs of the learners. For example, surrounding literacy or problem-solving skills. These tools run on expensive, specialized hardware that families or school districts are unable to afford. The tools are ineffective without educator support, or the tools cover out-of-date content compared to the state of the art in computing. I believe that we can address these gaps in access by taking an interdisciplinary approach to the design and development of computing education platforms. By first studying the developmental capacities of young learners to engage with this content, and then designing and developing appropriate tools that directly address these findings, we can build software systems to support accessible computing education. Specifically, today I'll argue that cognitively appropriate and readily accessible computing education tools support children's engagement and learning of core ideas in computing. But what do I mean by that? By cognitively appropriate, I mean meeting the cognitive limits of users, for example, surrounding literacy or problem-solving skills, while still designing for the competencies that they do have, as illustrated in contemporary cognitive development literature. By readily accessible, I mean running on widespread general-purpose hardware, like smartphones or tablets, which are in 97% of American homes, rather than on specialized equipment, like robots or tangible coding tools. And by core ideas in computing, I mean both the key concepts of software development, like sequences, loops, or events, and the key practices of computer science, like planning, decomposition, abstraction, or iterative development. I'll provide evidence for this argument across two domains of computing education, computational thinking and artificial intelligence. And I will show how we can leverage conversational AI to create new paradigms in computing education, how we might extend this voice-based approach into a multimodal system, how children began to think about and conceptualize this kind of voice-based AI, and how we can build on top of existing infrastructures in computing education to educate students about AI. So starting with computational thinking, I'll demonstrate how we can teach computational thinking concepts to pre-literate children through storytelling using a voice-guided system called StoryCoder. So despite a recent emphasis on computing education for all, many of our youngest learners lack the advanced literacy, numeracy, or fine motor skills needed to use most traditional programming environments or computational thinking tools. A number of successful solutions for young children seek to bypass these literacy requirements. But these approaches often depend on a knowledgeable teacher for students to make meaningful progress in the case of block-based programming environments, or they require expensive and specialized technologies that are not readily available to all students in the case of tangibles or programmable robots. And although these tools support children's engagement with computing concepts, they often lack scaffolding for key practices, like decomposition. This design leads to bottom-up development and non-reusable fine-grained code, both of which are contrary to accepted practices in computing. But why is this the case? As it stands, many of the computer science education tools today are informed by Piagetian psychology, which suggests that children cannot reason abstractly until they're much older, around age 12. But my own work into children's capacities for problem decomposition joins a growing body of literature in the cognitive development space in telling another story about children's abstract reasoning skills. We leveraged a block building paradigm, and we asked children to reconstruct target structures from components. And we showed that, contrary to prior belief, decomposition skills do begin to develop by early elementary years. We therefore aim to directly support children's engagement with decomposition and abstraction while still introducing computing concepts like sequences and loops. So in this project, I demonstrate that children can learn computational thinking concepts in a way that simultaneously builds literacy skills by engaging with these ideas through storytelling. And further aligning with the oral traditions of storytelling, it's possible to introduce these computing concepts using a smartphone-based voice interface, which allows even pre-literate children to engage with this material without necessitating any specialized hardware. Finally, we do so in a way that scaffolds decomposition and abstraction while children learn computing concepts. From a curricular standpoint, we pulled our computational learning goals from Brennan and Resnick's 2012 computational thinking definition, which was developed for elementary school learners using Scratch, and from the K-12 CS framework. So cross-referencing these lists, we identified 4 key computing concepts: sequences, loops, events, and data, or variables, and 4 key computing practices: decomposition, abstraction, planning, and computing for self-expression. From a storytelling perspective, prior work has shown that early exposure to storytelling can improve children's reading, writing, listening, and oracy skills later in life. And specifically, reading stories aloud to children and explicitly teaching them story structure improves language comprehension and reading comprehension skills later on. So we aim to support these activities as well. To also ensure that our solution was grounded in the needs of teachers and learners, we engaged in Needfinding. We conducted semi-structured interviews with 11 participants and 2 classroom observations, as pictured in this photo on the right. And through this formative investigation, we identified 3 key design objectives beyond these curricular goals. First, we found a need to make tools accessible to children in terms of literacy for children who are non-readers and financially. We turned to voice interaction to support these young pre-literate learners in expressing complex or abstract ideas. And we built a system that could run on general-purpose hardware, smartphones. We found a need to make tools approachable to children, educators, and parents who might be experiencing self-doubt in their ability to learn or teach about computing. We aim to make our solution approachable even to reticent learners by using storytelling as a really familiar domain by which to teach these computing concepts. And finally, educators mentioned a need for long-term engagement. They suggested that personally meaningful projects could drive this engagement by allowing students to get invested in what they're actually working on. We therefore gave children agency about the kinds of stories that they could tell to ensure that the system connects to their interests. Putting this all together, we built StoryCoder, a voice-based smartphone application that introduces computing concepts to children through storytelling games. StoryCoder consists of 6 voice-based user flows, 2 targeting storytelling, which guide children in creating and listening to stories, and 4 story games that each use storytelling as a domain to learn about a specific computational concept. So a child might begin by engaging with the create a story flow. So in this flow, the app scaffolds decomposition and abstraction as the child generates a story plan. It does so by asking about the main character, the location, and the problem in the story. And then it encourages the child to tell the story with a beginning, a middle, and an end.
Okay, create a story. Before you tell the story, let's make a story plan. I'm going to ask 4 questions. Question 1, is the star of your story a person or an animal?
Animal.
Awesome. What kind of animal?
A dog.
Sounds good. We'll tell a story about a dog.
So once a child has created their story, they can listen to it, or they can play with that story to engage with key computing concepts, sequences, loops, events, and variables, through one of 4 computational story games. For example, in word events, a child can pick a word in their story to be an event, which can then trigger recorded sound effects.
Awesome. We will record a sound effect for the word event, flute. You can record any kind of noise. As soon as you tap on the microphone, start recording your noise.
Doo-doo-doo.
Whenever we hear the word flute, we'll play the sound.
Doo-doo-doo.
So every user flow underwent a design process that included Wizard of Oz testing prior to implementation and iterative testing after development to further improve our system's design. We then conducted an evaluation of the system with 22 children, aged 5 to 8. Half of these children were female and half were male, with 7 entering kindergarten and 5 entering each of 1st through 3rd grade. Children came from 8 different US states, had reading levels ranging from pre-reader to early fluency, and had no prior exposure to computer science. Each child participated in 4 60-minute sessions over Zoom on 4 consecutive days. So on the first day, we dedicated the session to app setup and pre-assessment. On the second and third day, children played with the StoryCoder app. And on the fourth and final day, we completed post-assessment. We specifically sought to answer 8 research questions that related to our overarching objectives in the development of story comprehension, computational learning, and attitudinal shifts towards computing. For today, I'm just going to go over 2 of these in detail, one related to storytelling and one related to computing. So beginning with storytelling, we asked, do children tell better stories with the scaffolding provided by the system? We asked children to tell 3 stories over the course of the study. First, in pre-assessment, they told us a story without any constraints, which we called the free storytelling condition. So we asked them, tell us a story about anything. Also in pre-assessment, they told us a story in which we verbally provided the same constraints that they received from the guidance in the app, which we call the constrained storytelling condition. And finally, children told a story during gameplay, our in-app condition. So we asked if the planning activity, or the constraints provided therein, would help children to tell better stories overall. We scored these stories by using the index of narrative complexity, which is a 13-item rubric that was designed as a progress monitoring tool, so to compare a child's stories to their own former stories. And what we found is that children told significantly better stories with the planning guidance provided by our app than they did without such guidance. So we see that stories told in pre-assessment without any planning scaffolding are on the left, and we can see the increase in scores in planned stories on the right. I'll note, though, that this effect is specific to older children. This might be because the majority of the younger age group had yet to even start kindergarten. With the beginning of formal schooling, we see a rise in related skills like planning or auditory memory. So the lower scores in that group might be as a result of this. Looking next to computing, we also asked, can children recognize the computing concepts in a new context, specifically scratch animations? So for this recognition task, we first explained that my friend, Sarah, made a new game, and her game taught the same 4 ideas as StoryCoder, except her game uses animations instead of stories. Another child, Johnny, played this animation game. He picked an animation to start with, and then he changed it just a little bit as he was playing. So we played children a before animation and an after animation, and we asked them which game had Johnny played. We ran 8 trials, 2 covering each concept, where one of those trials was a near transfer example of that concept, and the other one was a farther transfer example, relative to the presentation of that concept in the app. And we'll report percent correct here. If a child had learned nothing, we might expect that their responses would resemble the responses of a child who was guessing. They would show chance-level performance, which here is denoted by this dotted blue line. Overall, though, we found that children were able to recognize the 4 computing concepts. Both younger and older age groups performed significantly above chance on this concept recognition task. So in this work, we developed StoryCoder. And through it, we showed that pre-literate children can use a conversational voice interface to effectively learn computational thinking concepts through storytelling games. StoryCoder demonstrated the potential for voice interfaces in delivering educational content. but it also came with its own set of challenges. So we continued on to build a more robust multimodal extension of the system, which we're calling Visual StoryCoder. So in this follow-up, we developed a system that supported the creation of more complex stories and also included more concrete learner engagement around computing practices like decomposition and abstraction. StoryCoder showed that voice interfaces can be successful in delivering instruction. But voice interaction also presents challenges to cognitive load and navigation, which can prevent the creation of more complex stories. To use a voice-only app, a child needs to remember everything that they've already done in order to decide what to do next. And if they want to navigate elsewhere or go back, it's a lot easier to do that by pressing a button than it is to navigate by voice. Block-based programming interfaces, on the other hand, present continuous cues and reminders through a graphical interface. But these interfaces can suffer from a lack of built-in instruction, which can make it hard for children to succeed without access to educator support. So we developed Visual StoryCoder, a multimodal system that blends the strengths of these approaches to overcome their respective weaknesses. This system more actively engages children with decomposition and abstraction, while also supporting the creation of more complex stories. So this system is aided by Flo the fish, which is an instructional voice agent you see in the top left. This child has completed the planning process. She's about to start telling her story, so we can watch her make her first chapter. Oh.
I'm excited to hear your story about
It's about a basketball player.
at
A basketball court.
hit the check mark to get started. Awesome. Our story will have at least 3 chapters, a beginning, a middle, and an end. To get started, drag a dark green chapter block into our workspace. Just like in books, our chapters will hold pages. Pages are where we'll add words and pictures to our story. We can add pages to a chapter with a page block. Great. Every page should have both words and pictures. Tap on that page to start editing.
Oh.
In the beginning, we talk about the star and the location of the story. Can you tell me the beginning of your story?
This is about a...
Awesome. Now let's draw a picture for this page of your story. You can drag stamps of the star, location, and problem into the picture for this page, or you can use the toggle to switch to draw mode. Thanks for telling me about the beginning of your story. When you're done with the beginning, tap on the smiley face on this chapter and save it by choosing an emoji. Now that your chapter is saved, we can add it to your story. Your story is at the bottom of the screen. Tap the plus button to add a chapter to the story and select the emoji for the beginning chapter.
So through this interface, a learner specifically engages with abstraction and decomposition by modeling their story, or modeling their program as a story, and then by breaking that story down into chapters and chapters into pages. By defining chapters with emojis and then including those chapters in the main story, they're engaging with activities akin to defining functions and then calling those functions from their programs. Once they've created their full story, they can again engage with loops, events, and variables. For example, they can turn the stamps that they included in their story's pictures into variables and change them out for new pictures. So this girl decided that it was obvious that her story about a basketball player took place at a basketball court, and she wanted to be more specific. So she changed her location, so her story took place at a basketball center, rather than at a school, for example.
A variable is a thing that can change, but we can only change one thing for another of the same type. We can make the picture stamps in your story into variables. Now can you draw a new picture of the location? Cool, now you're using a variable in your story. We have changed out the stamp anytime you used it in your story pictures.
And then we can see that change manifest in her story pictures wherever she used that location stamp. So we conducted a between subjects evaluation of the system with 24 children, aged 6 to 8. Half of them use Visual StoryCoder, and half of them use Scratch Junior, which is a leading block-based programming app for this age group. 6 first graders and 6 second graders participated in each of these conditions, and none of these children had any prior instruction in computer science. Children participated in 2 60-minute sessions over Zoom on 2 consecutive days. On the first day, they independently played with the app. The experimenter wasn't allowed to provide any support or answer any questions. On the second day, the child received instructions on 4 concepts in the app. Those 4 concepts were the same across all children, but the instruction was rooted in the project that they'd created on day 1. Then they had another 30 minutes to create a brand new project, except this time they were allowed to ask questions. So before going further, I do want to lend some context to this comparison. In Visual StoryCoder, children program stories using chapter and page blocks, and an agent provides just-in-time instruction. In Scratch Junior, children program animations by controlling the motion of characters using code blocks. There's a tutorial video in the app, which all children in this condition watched at the start of session 1, but there's otherwise little built-in support. Through this comparison, we looked to answer 3 key research questions related to our overarching objectives in supporting at-home learning through built-in instruction and an emphasis on computing practices. So we asked, does built-in instruction and a focus on decomposition and abstraction affect the degree of system understanding among users and the quality of code artifacts that they produce? Does experimenter instruction and question answering in session 2 impact this system understanding and code quality? And how engaging do children find these 2 systems? Again, for today, I'm just going to go over 2 of these, so we'll talk about system understanding and code quality. So we looked at 2 quantitative metrics and 2 qualitative metrics to answer these questions. First, we evaluate the degree of understanding of key aspects of the system, scored from a rubric based on a post-session quiz. We also quantified the quality of the code artifacts that children produced based on a rubric for scoring Scratch Junior projects. This rubric was pulled from prior work. Then we created a direct mapping adaptation of that rubric to score the Visual StoryCoder projects. We collected qualitative data from experimenter observations during gameplay, and from an artifact-based interview at the end of each session, in which we asked children about the projects that they'd made. So looking at our data, we see an unsurprising significant effect of system understanding by session. So as you see here, we see an increase in system understanding in the second session, after children have had an opportunity to familiarize themselves with the app, after they've received instruction, and after they've had a chance to ask questions. And I'll note that here and on all graphs in this presentation, error bars are 95% confidence intervals. Interestingly, though, we also see a significant interaction between app and session. Children using Scratch Junior had a much larger increase in understanding from session 1 to session 2, whereas this was not so much the case with Visual StoryCoder, where the change in system understanding after instruction was much smaller. We interpret this as support for the ability of built-in instruction to teach a child about a system in Visual StoryCoder, whereas Scratch Junior really benefited from that instruction educator support. Qualitatively, participants spoke about how the instruction was important to them in figuring out how to use the app. So when asked what they did when they got stuck, one 8-year-old using StoryCoder said, "It was important for me to know to click on the fish when I didn't know what to do. Of course, in our app, clicking on the fish would make it repeat its instructions." On the other hand, children using Scratch Junior talked about being confused, clicking about randomly when they didn't know what to do, or just ignoring the parts that they didn't understand. A different 8-year-old said, "When I was confused with something, I kind of just ignored it and did something different." Based on this qualitative data, we believe that built-in instruction was critical to the system understanding in Visual StoryCoder. Next, we look at code quality across sessions. We find that the average code quality for Visual StoryCoder is higher, but not to a statistically significant degree when aggregated across sessions. But we also see a great deal of variance in code quality scores in session 1. In Scratch, there were children who didn't touch the code blocks at all, And there were children who dragged every single code block possible into their projects just to see what they would do. Our rubric was based on the presence of code blocks and projects, so that contributed to a lot of variance in Scratch Junior. In StoryCoder, we had multiple children who didn't get through the full user flow of the app in the allotted 30 minutes because they spent so much time telling their stories. This means that they didn't get a chance to engage with loops, events, or variables, which also means that these concepts weren't present in their projects in this first session. So as a follow-up, we look only to session 2, when students have familiarized themselves with the app and what it can do, and we find that students using Visual StoryCoder do create statistically higher quality stories. We attribute some of this difference to the app's scaffolding around planning. Children using Visual StoryCoder talked about the need to plan their stories, whereas those using Scratch Junior often mentioned making up their story as they went along. When asked how they got their idea for their project, one 6-year-old using StoryCoder said, "I got started by thinking who was in the book, and then I was thinking about what they would do, and it was important for me to have a plan." On the other hand, one 7-year-old using Scratch Junior said, "I went to the plus button, and I saw a really pretty flower, and I wanted it to be part of my story. So then I thought of that, but I technically made it up as I went." Differences in this reported planning behavior provide evidence for how Visual StoryCoder can support children's planning processes. So overall, with Visual StoryCoder, we demonstrated how multimodal interfaces with built-in instruction help learners better apply computational thinking practices. Shifting gears now to look to the domain of AI education, we first ask how young learners intuitively think about conversational AI, like the kind they interacted with in StoryCoder. So when we were developing StoryCoder, we time and again heard stories from parents about their children's interactions with conversational AI. There was a 4-year-old who, when told his entire family was going on vacation, asked, "Is Google coming too?" And there was a 3-year-old whose family had a Korean rice cooker, and every time the rice was ready, it would say in Korean, "The rice is ready." And this 3-year-old would go running over to the rice cooker to talk to her grandma, the only Korean speaker in her life. So with virtual assistants everywhere, we began to question, when a young child begins to interact with this kind of technology, what is it they think they're talking to? And how do they extend their cognitive capacities for reasoning about other human minds in order to reason about this kind of AI? So we know that humans have robust systems for identifying living and non-living, for distinguishing between agents and objects, and for reasoning about the minds of other humans. But conversational AI falls into this unusual psychological pocket of exhibiting many of the key behaviors of living agents, and humans in particular, while being distinctly non-living objects. By preschool, children's speech is coherent enough for them to begin interacting with conversational AI. At this point, children have a robust understanding that agents are goal-directed and have internal responses to external behavior. They're also beginning to understand that agents can have knowledge separate from themselves and beliefs that differ from ground truth, which both influence this goal-directed behavior. And further, prior work has shown how children extend this reasoning to non-human agents. But it remains unclear. What of this intuitive psychology might they leverage in interactions with conversational AI? And how might they use these cognitive capacities to build mental models around this kind of AI more broadly? Limited prior work exists in this space, but in one study, children aged 3 to 6 interacted with Google Home for a brief period before being asked to draw Google. Notably, before age 6, some of those drawings contained a human-like feature, like eyes or a mouth. Here we see that one child said, "Google is a girl, but she doesn't have any arms." After age 6, though, none of those drawings contained any human-like elements. So we initially piloted a similar task, and we found similar trends. But this study doesn't ultimately help us understand how children represent the mental states of these devices to reason about their behavior. So we ask, how do children reason about the minds of virtual assistants? One possibility is that children reason about these devices in the same way that they'd reason about human minds, before they begin to distinguish the nuances of these devices from the minds of people. So let's look at how children reason about the minds of people. This paradigm in particular rests heavily on something called false belief. So let me first explain that. As an example, this is Rachel. Rachel brought raisins to have during snack time. Rachel's in a room with 2 containers, and Rachel decides to put her raisins in the blue container. Then Rachel goes away. Now, while Rachel is away, Joe comes in. Joe decides to play a trick on Rachel. Joe takes Rachel's raisins out of the blue container and moves them to the green container. And then Joe goes away. So now Rachel comes back in. Where will Rachel look for her raisins? The blue container or the green container? Hopefully, you all realize that in this scenario, Joe knows that the raisins are in the green container. But Rachel falsely believes the raisins are in the blue container. Adults would understand that these 2 people have separate minds with separate information. Adults would answer blue container. Your average 3-year-old, though, would answer green container, because 3-year-olds typically fail to represent others' false beliefs. This comprehension of false belief is a key marker in children's understanding of others' minds that we build upon in our study. So what does the developmental trajectory of false belief understanding look like? Something like this. 3-year-olds typically fail false belief tasks. They give responses consistent with the understanding that Rachel and Joe share a mind. They would say that Rachel would look for her raisins in the green container. In the years following, though, we see a sharp increase in understanding, such that children demonstrate adult-level performance on these false belief tasks by age 6. 6-year-olds would give answers consistent with the understanding that people have separate minds, and they would say that Rachel would look for her raisins in the blue container. So returning to our question, we asked, how do children reason about the minds of virtual assistants? Or more specifically, how do children extend their false belief reasoning to reason about virtual assistants? So we presented children with a false belief task. So here, Scotty in the dark blue shirt goes into a room and tells one person that his favorite song is the Itsy Bitsy Spider. Then he goes into a different room and tells a different person that actually his favorite song is the Wheels on the Bus. And finally, he returns to the first room and asks that first person, can you please play my favorite song? Our key question is, what song will this person play? Hopefully, you all say this person will play the Itsy Bitsy Spider, the first song, because that's what Scotty told this first person in this first room was his favorite song, even though he later corrected that information for a different agent. Your average 3-year-old, though, would say that this person would play the Wheels on the Bus because of their lack of understanding of false beliefs. Now, imagine that Scotty was talking to smart speakers instead. The interaction is the same. What song would the first speaker play? The answer maybe isn't as clear, but if these 2 devices are in the same household and connected to the same account, you might infer that the first smart speaker would actually have the updated information given to the second smart speaker and play the second song, the Wheels on the Bus. Turns out adults understand this. So here we ran this study online with 59 adults on Prolific, and we plot the proportion of adults in each condition answering with each song. In our person condition, in gray, adults say that the person in the first room will play the Itsy Bitsy Spider, the first song. But in the AI condition, in blue, we see that adults say that the smart speaker in that first room will play the second song, the Wheels on the Bus. A replication of the study yields the same results. Adult responses in the person condition are consistent with the understanding that people have separate minds. But in the AI condition, responses are consistent with the understanding that smart speakers have a shared mind, or a connected backend. So we've also run 135 children, aged 3 to 8, through this task conducted remotely over Zoom. As a reminder, I've plotted adult-level performance as points here on the right. Again, the person condition is gray, and the AI condition is blue. So what do children do? Looking first to the person condition, we see that our data follows the false belief trajectory that I previously showed. 3-year-olds are answering incorrectly on this task because of their failure to reason about false beliefs, but by age 6, children are demonstrating adult-level performance and giving responses consistent with the understanding that people have separate minds. Turning to the AI condition, we might expect the curve to look something like this green curve that I've drawn on the graph. Children might start in a similar place with a lack of representation of false beliefs. The curve might bend upward as children begin to understand false belief, but it should ultimately end up down at the bottom, somewhere near adult-level understanding. Looking at our data, though, we see that in the AI condition, if we first look at children who do not have connected smart speakers at home, their responses again follow the false belief trajectory. Children in this group have not begun to differentiate the mental states of these devices from those of people, perhaps because they've not had enough experience with these devices to start building separate mental models. But if we look to children that do have connected smart speakers at home, we see that even children with extensive experience with these devices don't give answers that anywhere resembles adult-level understanding. So this is an example of AI that these children do interact with. But we undoubtedly see a clear difference in understanding between even 8-year-olds and adult-level performance. So returning once more to our research questions, we find that children's reasoning about the mental states of these devices follows in line with their reasoning about humans, at least through age 8 in this false belief task. Experience with connected smart speakers at home may have some impact on this understanding, but adult-level understanding doesn't emerge until sometime between age 9 and 18. Therefore, this work demonstrates that children's misunderstandings of AI systems suggests a need for AI education that helps to facilitate more accurate mental model development. Which leads me to the last project that I'll discuss today, an accessible system for AI education. And I do want to mention here that this next section contains work I did while working at Apple. So conversational AI is just one example of the kinds of systems, AI-driven systems, that kids might interact with. With the increasing prevalence of AI and machine learning in everyday life, we see that researchers and educators have started advocating for studying AI machine learning education as a complement to contemporary computing education. Today, robotics is one of the main entry points to computing. But while state-of-the-art robotics makes heavy use of AI and machine learning, K-12 robotics education today centers on mechanical engineering and imperative programming. This makes robotics an ideal context for introducing AI and machine learning to students. In particular, robotics is a natural fit for exploring reinforcement learning, which is a type of machine learning used in state-of-the-art robotics research. But reinforcement learning also drives some of today's day-to-day AI technologies that young children might be interacting with. Reinforcement learning has been less studied in the AI education space, but we also hypothesize it's conceptually easy comparatively to understand. Although robotics is relatively widespread, the cost of specialized hardware can be a huge barrier to access. So we also aim to create a more accessible robotics education by leveraging virtual robots that run on general-purpose hardware, tablets, and then bringing these robots to life using augmented reality. So in our work, we built ARtonomous, a robotics education experience for middle school students that addresses cost barriers to wider implementation by leveraging general-purpose hardware, and tests our conjecture that young learners can develop a conceptual understanding of reinforcement learning. To make sure we're all on the same page, I'll go over the concept behind reinforcement learning. Reinforcement learning is a machine learning training method based on rewarding desired behaviors and penalizing undesired ones. Or in other words, it's learning from rewards and penalties. Imagine training a dog. If a dog does something good, you might give it a reward, like a treat. If it does something bad, you might give it a penalty, like scolding it. Over time, that dog might become more or less likely to take a similar action in a similar situation. In the context of robotics, we can train a robot to navigate using simulations. When it does something good, we can give it points. When it does something bad, we'll take away points. In the ARtonomous app, students use reinforcement learning to train autonomous navigation models that integrate with event-driven code, allowing the user to customize their robot's behavior. Users are able to create tracks for their robots, train virtual robot agents to navigate these tracks using reinforcement learning, view simulations and visualizations of that training, and combine their models with code for flexible closed-loop robotics. So for the purposes of a demo, let's imagine that the student had this objective. They wanted a school bus robot to navigate autonomously around a bus route track. It should stop, flash its lights, and load passengers at every one of the red bus stops. And it should stop, unload all its passengers, again flashing its lights, at the yellow school bus stop at the bottom. So our user here has already recreated this bus route track in the app, and they start with a partially pre-trained robot. That means that if we test this current robot on the bus route track, we'll see that it knows it should be moving forward, but it's not very good at following the track yet, especially on tight turns. Going back, we can create a track to train our robot on that targets an issue that we've identified. So this square track gives the robot practice on those tight turns. So we save the track and kick off that training. Training can take some time, so speeding it up a bit here, we see that the car does get better over time. And on episode 50, it actually does pretty good. So next, we can bring this experience to life and check out a simulation of that 50th episode in augmented reality. Finally, returning to our bus route track for another test run, now that we've done some training, we see that our robot does better. But we also see that it still has some training to do. Once students have a working model, they can switch over to the code editor, which will load up the course and the robot navigation model on the right, and present users with the development environment on the left. This interface contains a function library that students can use to customize robot behavior during event-driven callbacks. For example, they could change the robot's color to yellow at the start of the run, or flash lights and pick up a passenger at a pickup point. We evaluated this experience in 90-minute remote sessions with 15 middle school students, age 11 to 14. 6 of these students were female, 9 were male, and all of these students had prior experience with robotics or hardware. After an introductory phase, students trained a robot to navigate and wrote code to achieve that school bus objective that I showed in the demo. We then concluded with about 10 minutes of questions and feedback. So we measured participants' developing understanding of reinforcement learning, their engagement with the apps, and their curiosity to learn more about machine learning. Across several measures, we found that participants developed an understanding of reinforcement learning. For example, when asked what reinforcement learning is, 93% of participants described reinforcement learning as an agent learning from rewards, penalties, or experiences for future novel situations. For example, one 12-year-old said about reinforcement learning, it's when you have something do something, and it takes your input and it does an action, and then you give it like points or not points or whatever, so that it knows when it did something wrong and when it did something right, so they can try to do the right thing next time. Looking at participants' engagement, we took the 7 prompts from the Giggle Gauge metric, which is a validated self-report engagement metric from prior work. Participants indicated their agreement with each prompt on a scale from 1 to 7, and we report a mean engagement score of 6.17 out of 7, which indicates relatively high engagement. From a curiosity standpoint, we asked students their level of agreement with the statement, I would like to learn more about reinforcement learning. Here they report a mean score of 6.47 out of 7, and all children gave a score of 5 or greater, indicating that they all agreed with this statement. So through this work, we show how virtual robotics platforms introducing reinforcement learning to young learners can create authentic and adaptive learning experiences and increase access to robotics education. Overall today, I've explored how we can leverage voice interaction to create new paradigms in computing education that are appropriate for pre-literate learners. How we can extend that approach to even better support the learning of computational practices. How children begin to think about and conceptualize this kind of voice-based AI. And how we can build on top of existing infrastructures in computing education to educate students about AI. In doing so, I've demonstrated how cognitively appropriate and readily accessible computing education tools support children's engagement and learning of core ideas in computing. And I'll be happy to take any questions. Yeah.
Are any of these tools that you built available for public use for children to use?
Not currently. So for the purposes of creating a research prototype, we're building something that's kind of robust enough for 50 participants in a user study. To then go on and release that publicly would require a lot more development work, which is in process, but hasn't happened. I'll also mention that a lot of the kind of back-end speech processing that happens runs on, right now, Google Cloud. And we chose that because that's the system and software that best understands young children's voices. But to then release that publicly, every kind of speech-to-text translation we do and text-to-speech costs money. So for the purpose of our 50 participants, it's like $6. But if we were to release it publicly, it would be used by a lot of people, potentially. It could get really expensive very quickly. Yeah?
So one really cool thing in all the research is using many different modalities to teach students, like voice for AR. And I'm curious, both concretely in the AR example, did you see any specific evidence that having the AR track was valuable compared to just having them see the 2D visualization? Like, if there's anything extra they got out of that? And also more generally, what are other modalities you're interested in exploring for other computational thinking or learning experiences that haven't been as widespread?
Yeah, so for the purposes of the study that we ran, we weren't able to test the AR features. And that was a deliberate choice, because in order to use those AR features, you have to have a really up-to-date iPad. But we wanted to make sure that we could be more inclusive of participants, and we emphasized or focused our recruitment on that. So to run those studies, if students had the iPad or the laptop that could run our software, then that's how we ran the studies. But for students who didn't, we were able to screen share a simulator of an iPad and allow them to interact that way. So in the study we ran, we actually weren't able to test the AR features. There's some prior work that shows increased engagement when children or learners learn and use AR, but that's actually one of the future directions that I'm excited about pursuing, is kind of how we can better integrate AR and then study AR in an educational context.
Okay, we have a question on the
Hi, can you hear me?
Yes.
Great. I've just noticed that a lot of the, what do you call it? The voices that were in the AI speech software were, I guess, more artificial, and maybe have had the cadence that might not be necessary for a human. Do you think that this generated text-to-speech may have impacted, children's ability to differentiate on, like, whether this thing was like of a shared mind or not, because it kind of sounds like it's clearly an AI generated voice.
Yeah, so there's a few different voices we heard in the presentation today. So in the software apps, the StoryCoder apps that children use, those were Google's text-to-speech voice in the first app, which is quite artificial sounding. And then the second app used Google's WaveNet voices, which actually sound a lot more realistic. For the purpose of the video, I sped it up so you weren't listening to a very slow agent talk. So in speeding it up, it became a lot more artificial. Those WaveNet voices are surprisingly realistic and are the voices that are on Google Homes, for instance. So as to whether those artificial voices would impact children's understanding, it's quite possible. But even with that distinction, so even if children are using or are recognizing that there's a difference in this voice from a regular human voice, what our data is showing is that they're not reasoning about these devices kind of differently than they do from a human mind, which is actually really surprising for us. Does that answer your question?
Yeah, it does.
Perfect.
Okay, I think in the interest of time, because the class is over, we'll wrap here, and I think Griffin will stay around for a few minutes and take a few questions, and then the committee's going to move to a private meeting. So thank you, Griffin, and congratulations.